Okay, very good morning to all of you. So, if you have been given a data set and if you wish to find a smooth curve passing through them, is wish to say you have the data set like x and f. So, f is a function. You may not be aware about the function, but you may aware about the experimental data. So, you add some points x0, x1, and so on, xn, and these are okay, and the points at f values at x0, x1, x2, xn's are we denote by y0, y1, and so on, yn, or simply as you can say sometime we are also denoted by f0, f1, fn, or these are the, you can say, abused notation in mathematics. Okay, this f of x0, this f of x1, f of x1, and so on. This is f of xn. So these the second row we call as ordinates, and the first row is called the nodes, at which you have the values. So what you wish to do in interpolation is, since you have the data in you can say xi comma fi, you have the n plus 1 data points, 0 less than equals to I less than equals to n. It is taking, or I is only positive, or you can say non-negative integer. Okay, and you wish to fit this data in a smooth curve. The smooth curve is very familiar with us, is as a polynomial. Okay, so which you can differentiate as many time you can, it is continuous, differentiable, there are so many nice properties are attached with it. Okay, so not only you may interest, so you have a let's say some point is there, let's say here is this is 1 comma 1, and let's say this is 2 comma 2. So you if you fit this, you can fit by a polynomial, by a you can say this is a straight line passing through this. So y equal to x, it is very well known among ourselves. Okay, so you can fit into this as well, and you can fit into a quadratic curve. Okay, passing through these two. But our wish is to find a polynomial of degree. Okay, a polynomial of degree at most n, with means with less degree as much as possible, at most n. So with n plus 1 data points, so because with the 2 points you can definitely construct a lowest degree polynomial is of degree 1. Okay, with the 3 points, if you include one more point, you can construct a polynomial of degree means at most 2. Okay, right. And not only the smooth curve, okay, not only the smooth curve, you may wish to know, so means like suppose you have been given a data, okay, and you wish to know the values at some in between some points. So let's say some x here, okay, is this x is in between, so you can have let's say for generalize, you can say x0 equals to a, and then xn is equals to b. So for generalized point of view, let's say x0 is a and xn is b. So what we wish to find, the value of function f at some point x. We want to predict the value, reasonable value, okay, for some x in open interval ab. Okay, so first problem is to identify a polynomial of degree at most n. And then means if f is not known, what is our target is to get a better approximation. Okay, so how, in what terms we will say this is a better approximation? Okay, means it be completely based on the error included in the predicted term. So that also we need to understand. Okay, so so here what the px, so we wish to know the function value at some, we wish to predict the value of function f at some point x in between the ab. So what will be the property we wish to have for p is it should fit the data. So p of xi is equals to fi. that at least for 0 less than equals to I less than equals to n. Then we have seen the existence of this interpolating polynomial. Okay, existence of interpolating polynomial, and we have seen the two forms. One is Newton form and another is Lagrange's form of interpolating polynomials. Okay, so let's go with one example here. So let's say this is example one, and by our the knowledge what about the Newton's form and Lagrange's form. Okay, so let's have this construct an interpolating polynomial. Construct an interpolating polynomial which fits the following data. Which fits the following data. Following data. So we in it is in given in table form. So at so x and f values. So at x naught, so 1, 2, and 4. Let's say 3 points are given. At 1, let's say f value is 2. At 2, let's say it is 5, and at 4 it is 17. Okay, and then we wish to also predict. Okay, we also wish to predict the value of f at say x equals to 3. So we are looking for the value of function f at in between of the points which has been given. So between the interval 1 to 4, you can say. Okay, so so we have two ways. So we can find Newton's form as well as Lagrange's form of interpolating polynomial. So for so you if I wish to go for it, so let's say, so if I from the table x naught value is 1, x1 value is 2, x3 value is x2 value is 4, and the corresponding values are f naught is 2, f1 is 5, and f2 is 17. These are you can derive from the table. So for the Lagrange interpolating polynomial, so you need to first devise the cardinal functions. So cardinal functions, if you recall, are given by Li of x, that is equals to product of I equals to 0 to n, I naught equals to j, x minus xi. Right? So this is Lj of x. Yes, this is Lj of x, where j is running from 0 less than equals to j less than equals to n. Okay, right. So if you wish to go further, okay, so here I is, if you look at here, so here j n value is, if you see 0 less than equals to j equals to 0, 1, and 2. So n value is 2 here. Okay, so we are going to get a polynomial of degree 2, right? Quadratic polynomial. Okay, so if I go for finding L0 of x, L0 of x, that is equals to, you have x minus x1 into x minus x2. If I go with the previous notation, that is divided by x naught minus x1 into x naught minus x2. Now you compute the values. So x minus x1 was 2 and x2 was 4. So x minus 4 divided by x naught was, if I go back and check, x naught was 1. Okay, x naught was 1. So if so this is divided by 1 minus 2 times 1 minus 4. So that is equals to the denominator minus 1 into minus 3. So there is 3. So that is 1 by 3 times x minus 2 times x minus 4. So similarly, you can go for L1 of x, that is equals to, if x minus x naught into x minus x2 divided by x1 minus x naught. time x1 minus x2. And if you recall if you fit the values here, so that is x minus 1, x0 value is 1 and x2 value is 4, and not that x1 value was 2. So that is so here that is 2 minus 1 and 2 minus 4. So that is equals, so denominator is 1 into minus 2, so minus 1 by 2 times x minus 1 into x minus 4. Similarly, you can go for L2x as well. So L2x was x minus x0 into x minus x1 divided by x2 minus x0 into x2 minus x1. So if you fit all the values, so you have x minus 1 into x minus 2 divided by, so x2 value was 4, so 4 minus 1 into 4 minus 2, so that is equals to, so 3 into 2 is 6, so 1 by 6 times x minus 1 into x minus 2. So we have all collected all the possible cardinal functions here. So therefore the Lagrange's form of interpolating polynomial is p of x is equals to f naught L naught of x plus f1 L1 of x plus f2 L2 of x. So you substitute the values of L naught of x, L1 of x, L2 of x here. Okay, and simplify it. So f naught value is 2. Okay, f naught value is, that is 2. F1 value from the table is 5. F2 from the table value is 17. Okay, so I'm going to give you the simplified form of it. Okay, so you can write the Lagrange form of interpolating polynomial, and so this is equals to, if I'm going to fit the data, so that is 2 by 3 times x minus 2 into x minus 4 plus this is minus, because minus 1 by 2 is there in L1, so minus 5 by 2 times x minus 1 into x minus 4, okay, plus 17 by 6 times x minus 1 into x minus 2. Okay, now see, if you want to derive the this final expression, okay, that I can give you, that is going to be some x square plus 1 if you write in the simplified form. Okay, now we also wish to predict the value of the function at 3, at x equals to 3. So since f is not known to us, so we definitely wish to predict the value, okay, f at 3, and that should be approximated by the interpolating polynomial. So predicted value is p of 3, and that is equals to 3 square plus 1, that is 9. So you see, for predicting the values, you no need to simplify this. Okay, you no need to simplify this. Okay, you can directly substitute the value x equals to 3 here, okay, and everywhere, and just simply multiply the numbers and find the final value. That also you can do. That's a very simple way. Okay, so this is the way you will predict the value. But we also now the next we are interested in what will be the error here. Okay, so whether this how much accuracy is there in terms of error when you are approximating the given function f by a quadratic polynomial. So you have, because you have given 3 data, so you can approximate by quadratic interpolation, and now you are interested in finding the what will be the error term, total error, we can say. Okay, so if I wish to fit the data by the Newton's interpolating polynomial, so you have to just simply, so in the Newton interpolating polynomial, so you need to create that divided difference table. Okay, so I will just quickly review how you will evaluate the divided difference table for the given data. So I have the, so I will write in the vertical form now, this data of x, f. So that was 1, 2, 4, and that is 2, 5, and 17. Now, first divided difference. Okay, so if I wish to go for first divided difference, if I explain correctly and you have got the in a correct way, so we are going to write in this. Okay, so you are going to use these two values. So 5 minus 1 divided by 2 minus 1. So means the means f1 minus f0 divided by x1 minus x0. So that is equals to 5 minus 1 is 4. 4 by 1 is 4. Another the second entry here in the this column is 17 minus 5. So that f2 minus f1 divided by x2 minus x1, that is 4 minus 2, and that is equals to this 12 by 2, that is equals to 6. Okay, now the next divided difference formula means it the next divided difference will use these two values, right? 4 and 6 here. So the difference of these two, 6 minus 4, means from the means you are going in forward direction. It's like 6 minus 4, not 4 minus 6. Okay, so 6 minus 4. So in the same way you are going to in here also forward direction. So here instead of means like 1 to 2 and 2 to 4, now you are going to consider this. You are skipping this 2 here in between, starting with 1. So 4 minus 1, that is 6 minus 4 is 2 by 3. Right? Okay, so this is these are the divided differences. Okay, first order, second order divided differences. And not that, so what you require in the Newton's interpolating polynomial, so if you go for this data, Newton interpolating polynomial, so p of x is equals to f of x naught, okay, plus x minus x naught time first divided difference, that is f of x naught comma x1, plus x minus x naught into x minus x1 times second order divided difference, x naught, x1, x2. Okay, and how will you extract it from the table is in this. So this is your f of x naught. This is first order divided difference. That is, this is second order divided difference. So you are looking in the, you can say, downward direction. Okay, when you are fitting the first divided, you are repeating the divided differences in the Newton's polynomial. So f of x naught is 2 plus x minus x naught is 1, right? So f of x naught comma x1 is 4. So second divided the first order divided difference time x minus 1 plus second order divided difference was 2 by 3 time x minus x naught. So that is equals to x minus x naught is 1. So x minus x1, and that is equals to 2. So this is the Newton's polynomial, Newton's form of interpolating polynomial. Okay, and again if you simplify it, you will again get the same polynomial x square plus 1, and you will give the predicted value will be 3, because the uniqueness is guaranteed. So you will have the different type of representation for an interpolating polynomial. So now what we are interested in, what will be the possible error in polynomial interpolation. Okay, right. Okay, so how will we go with it? So we are defining, so you can say that, so you have the, okay, you have the data set. So you have the data set of xi comma fi, where I is running from I equals to 0, 1, 2, and so on n. Okay, so you have the following data, and you have interpolated f by an interpolating polynomial p of x, which is of degree at most n. Okay, so right, okay, which is of degree at most n, and it satisfies the interpolating conditions that Pn of xi is equals to f of xi for all I is equals to 0, 1, 2, and so on n. Now what we are interested in to find the error in f, an interpolating polynomial at some value x that is going to be defined by f of x minus p of x, f of x minus p of x. Okay, so this is an error term. The error term. So we want to estimate this, and we will see the application of this as well. Okay, which this is very important for application point of view. Okay, so okay, so if so, not that if x is equals to, or x belongs to the data set x naught, x1, and so on xn. So x is equals to any of the nodal point. Okay, if x is in this set, then what will be the error? So en of f(x), or you can say at x equals to xi, is equals to f of xi minus p of xi. But you know that the interpolating polynomial that is here is n of degree at most n, which you have derived, is exactly fits this data. So x at xi and f of xi both are same, so this is equals to 0 if x belongs to this. So there is no error at the given data set. Okay, so for now, so let x is equal, x is does not belongs to this set x naught and so on xn. Okay, and moreover for generalization point of view, let x naught is equals to a and the end point xn is equals to b, and we don't know how these intermediate nodal points x1 to xn minus 1 are placed, whether they are equally spaced or they are arbitrarily spaced. We are not aware about it. So we will talk about this a little later. Okay, so let x does not belongs to this, and let, so that means we are talking about, so means this implies we are talking about the for x value belongings to open interval AB. Okay, and for this x belongs to AB, what will be the error estimate we wish to derive? Okay, right. So means, so let this implies x belongs to AB and it is fixed. Okay, so it is fixed. So at x means at some value x, we are try to estimate the error. So let this is now it is fixed. Okay, so now what we are going to do is we are going to derive a function. Okay, we can define. So let's define a function g of, let's say, t, because x is fixed. So g of t is equals to f of t minus p of t minus f of x minus p of x, f of x minus p of x time t minus x naught. So this is defined to capture some of the properties, okay, and to derive the estimate. So this you will, in a minute you will come to know, okay, that why this new function is defined, okay, so in this way. So this is x minus x naught, x minus x1, and so on, x minus xn. So we have defined for a t is in you can say AB or upper interval AB. So we have defined for any t a define a new function, okay, and we are going to now note down some certain properties of this function g. Okay, so let, okay, so now properties of g function. So let's look at it. Properties of function g. So we are going to see the properties of function g. So let t is equals to x. So you just set t equals to x. Okay. So then what will happen? G of x is equals to. So if you substitute t equals to x here and here, and x is fixed here, not that x is fixed value, and then you look at this this term. okay, this term which is here in the product of this f of x minus px. So when you replace t by x, this numerator and denominator term will get cancelled, and you will get it that is equals to 0, because t equals to x, this term is f of x minus p of x, minus f of x minus p of x is 0, because this term is 1. This term is at t equals to x is, this is value is 1. Okay, now you can say not let's say set t equals to x. Okay, now also for t equals to xi. So t equals to xi, what will happen? So f of xi and p of xi. So this term is also 0, and this term is yes, this term will what will be the factor here? Nothing, right? X is fixed numbers. F of x minus p of x is different from xi. So what about this product? So this product is xi is among x naught to xn. So one of the value is somewhere is, you can say, t minus xi in this product in between. So when you put t equals to xi, so this entire term will numerator becomes the 0 value. So 0 into, so what will be, so for this, so g of xi, if you note it down, that is equals to f of xi minus p of xi, the first term, first box term, and the second box term is as it is f of x minus p of x time the what is the product term, so that will be 0. So but since f and p are equals at x size, so this entirely is equals to 0. This is true for I equals to 0, 1, 2, and so on n. So this both properties will tell you that this implies G has n plus 2 zeros, right? Zeros in open interval AB, or you can say on closed interval AB. Okay, so n plus 1 is n plus 1 zeros are coming from this property for t equals to xi, and 1 0 and one more 0 is coming from there, this. So there are n plus 2 total number of zeros in closed interval AB. Now what I wish to know is I'm going to apply Rolle's theorem, which you have already studied in your first semester. Okay, so G has n plus 2. So what is the Rolle's theorem? So I am going to just give you Rolle's theorem. So what was the Rolle's theorem is? F is, let's say not F, okay. Let's say H is continuous on closed interval AB. It is differentiable on open interval AB. Okay, and so that's the first thing. The second property is it is differentiable on open interval AB, and third thing is h of A is equals to h of B. It meets, okay, means h of A is equals to h of B. Okay, at the end point the value of the function is same. So what we are setting, so this is so this then this implies there exists a point C in open interval AB such that h dash of C is equals to 0. Okay, means the slope at some point, there exists a point C where the slope is parallel to x-axis. Okay, so if I so now here I'm going to just for the using this for our this case, I'm just setting this for equals to 0. So this also remains true. So if you look at the graph in this case, so it's like something like this, and C is a point where this s dash of C is 0. Okay, so this is the Rolle's theorem tells you. Okay, right. Now how to use this in the this result? Okay, so G is so we have the G function which has n plus 2 zeros, at x0, x1, x2 and so on xn comma x. Okay, so if I have here, so let's say this is x0, this is x1, this is x2 and so on, and this is xn, and somewhere here is x, somewhere in between x is there. Okay, right, so these are n plus 2 zeros. Okay, now also note that, so if you look at this interval x0 to x1, okay, so you know g of x0 is equals to g of x1, that is equals to 0. Also see, before deriving the interpolating polynomial, we have made the assumption that the function is continuous. Okay, so f is continuous is assumed, and polynomial is a smooth function, so it's a very nice function, okay, which has very nice properties like it's continuous, infinitely time differentiable and so on. So if you go back and check here the definition of g, so if you look here, the g function, so f is continuous, p is continuous, so sum of two or difference of two continuous function is continuous. Okay, this is a number, so f of x minus p of x is a number because x is fixed, some value, number values. And now if you look at this here product, so the denominator is again a number because x is fixed and x0, x1, x2, xn are number, and x is different from this x0 to xn. Okay, and this above numerator is a polynomial of degree n plus 1, so it's again a continuous function. So you can so g is continuous. Okay, g is continuous, so this implies, so and g is continuous, you can say, on x0 to x1. Okay, so I'm just applying the Rowe's theorem on this interval x0 to x1. So for the Rowe's theorem, what another property required is differentiability. So that can be assumed. Okay, so that will, so because say polynomial is infinitely time differentiable. So if I assume that f is differentiable as many number of time as many we want. Okay, so we are attaching this property here, or you can say an assumption here, that g or f is differentiable. Okay, f is a smooth function, you can say. Okay, so let's say, so then g is differentiable on upper interval x0 to x1, then the Rowe's theorem implies there exists, so there exists some point, let's say c1, such that g dash of c1 is 0. G dash of c1 is 0. Similarly, the similar result you can apply on this interval, and you can get another 0 here, c2, then another 0, c3 of the g dash function. This is x3 here, and so on. So if I look here, xn minus 1, so here will be some cn. So see, these are n plus 2 points. Okay, so before there somewhere x is there, so we don't know x where it lies. So let's so you will have at how many number of zeros here? N plus 1 zeros. So I will denote it by some n plus 1, because see, somewhere x is here, so this is somewhere 0. Additionally, one more 0 is coming. So this, if you apply repeatedly, so if you repeatedly, okay, so if you apply, so Rowe's theorem applied repeatedly now, okay, repeatedly, what you will get means, see, then g dash function is having n plus 1 zeros. Now if you again apply the Rowe's theorem and use that f is again f is 2 time differentiable, you have n number of 0 for second derivative. Okay, so this so if I remark here, so g dash has n plus 1 zeros. n plus 1 zeros. If I again apply the Rolle's theorem again here, what you will get is, and you assume that f is 2 time differentiable, then g double dash has n zeros and so on. So what it will give you, if you apply the repeatedly, there exists a z in open interval ab such that the n plus 1th derivative, so at least 1 0 is there of n plus 1th derivative, that is the n plus 1 of z equals. Now we will calculate what will be the n plus 1th derivative of the function g. Okay, so if you use the property, okay, if you look at here the g function again. So if it is differentiable, if you are assuming that n plus 1 time differential derivative exists, means you are assuming that condition on f, that n plus 1 time you can differentiate. Okay, so differentiability on f n plus 1 time is assumed. Okay, that we will put them in a result. Okay, that in assumption part. Okay, so if you differentiate the first term, you will get the f n plus 1th derivative at t. So polynomial, this is p of t is a polynomial of degree at most n. So it's the difference derivative n plus 1 time it is 0. Okay, and this is a number. F of x minus p of x is a number, fixed number. You are differentiating this, so and f of x minus p of x divided by x minus x naught to x minus xn is a number, and you have in the numerator is a polynomial of degree n plus 1. Okay, and it's a, you can say, a polynomial with a coefficient, leading coefficient is 1. Okay, polynomial of degree n plus 1 with the leading coefficient is 1. Okay, so t minus x naught to t minus xn. So what will be the n plus 1 of derivative is n plus 1 factorial. Okay, so if I go on with this, so what it will be is, so gn plus 1 at z equals to 0 implies f n plus 1th derivative at z minus n plus 1 factorial, okay, time f of x minus p of x divided by x minus x naught to x minus xn is equals to 0. And if you solve it or if you simplify it, you will get the result. Okay, so you will get the result that, so from here if you simplify it, what you will get is f of x minus p of x is equals to f n plus 1th derivative at z by n plus 1 factorial time product of I equals to 0 to n x minus xi. Okay, so this will give you the error in interpolating polynomial of degree at most n at any point x. Okay, right. So if I collect all the things, okay, in a single result, so what its final result is in a theorem. If you see that, let f be a function in cn plus 1. So cn plus 1 is a n plus 1 derivative up to n plus, it is differentiable n plus 1 time, and its n plus 1 derivative is continuous. This is space. And let p be the polynomial of degree at most n that interpolates the function f at n plus 1 distinct points x naught to xn in the following interval. Now, then for each x, you will be able to find a point z, which certainly depends on x. Okay, such that this this result holds true. This which we have derived just now. Okay, now let's see how will we use this result, okay, as an application. Okay, now, so let's first see how would we find the bound on error. So let's have a bound on error. Means you have that en of f of x is equals to that expression. So if you take the magnitude both sides, so you are for finding the bound, you are going to take the magnitude and bounded by the largest value on the right side, right? So that is equals to 1 by n plus 1 factorial time mod of product of I equals to 0 to n x minus xi, okay, x minus xi time fn plus 1th derivative at z. See, again I'm mentioning that x is an interior point of x naught to xn. Okay, it's not the exterior point. So we are doing interpolation, we are not doing extrapolation. So this is what the difference here. Okay, so here, so if you bound it, so how would you bound it? So you have this is a polynomial which is continuous, uniformly continuous, and so on. And x lies between, you can say, x naught to xn. X naught is a and xn is b. So you can take the maximum, okay, and then you use the bound. So this is certainly less than equals to, okay, this is certainly less than equals to 1 by n plus 1 factorial, okay, and maximum of this, so mod of this product of I equals to 0 to n x minus xi, maximum over x belongs to x naught to xn, that is a to b we are denoting, time the maximum value of the second derivative in absolute sense. So maximum over, you have x belongs to n plus 1th derivative. Now, see, let's see now the error in linear interpolation. Okay, so these are n plus 1 data. So when, see, how would you find the maximum here? So if I wish to make a remark here, so this is a polynomial. This term is a polynomial of degree n plus 1. So you let's say this is some h. You find all the possible critical points, okay, by putting h dash of x equals to 0. Find all the critical points and see which at what point this is maximum, the product. Similarly for this here, so you see here for this term, you can always find the maximum, okay, but for the second term, which is in terms of n maximum over n plus 1th derivative, you may or may not able to find out, because the function may or may not be known to us. So definitely we have to replace it by some other estimate that we are going to learn means little later. Okay, so we call this as, so let mn plus 1 is equals to maximum of x belongs to close interval ab of n plus 1th derivative at x, that we are going to use the notation. Okay, and we are going to find the maximum boundary. Okay, so let's see error in linear interpolation. So let's say error in linear interpolation. So you have, it means if you're talking about linear interpolation, so you have the two data. So you have data with x naught comma f naught is given and x1 comma f1 is given. Means clearly n is equals to 1 here, right? We are not aware about the x1, we are not aware about the f function. Okay, so if you try to identify the bound of e, the error term, so mod of is n is 1, so e1 f at some x is equals to 1 by 2 factorial time x minus x naught into x minus x1 time f second derivative at z, where z lies between x naught to x1. Okay, so this is further less than equals to, as told, that this is less than equals to 1 by 2 maximum of mod of, so you are having here a mod here because we have taken already in the mod on the left side. So maximum over mod of x minus x naught into x minus x1 time maximum of the second derivative at z, second derivative at z. So z is some point in again x naught to x1. Okay, so I'm not mentioning here the interval, that you can fix it up. Okay, right. So so now what we wish to do is we are going to find the maximum of this. So this is a quadratic polynomial. So if I say this is g, so then if I put g dash of x equals to 0, so this implies g dash of x. So g of x is what? X square minus, so if I say this is x square minus x naught plus x1 time x naught plus x1 time x plus x naught into x1. And if I use g dash of x, so that is equals to 2x minus x naught plus x1 is equals to 0. This will give you x is equals to x naught plus x1 by 2. So we are talking about ordinary maximum, so not absolute or absolute. We can talk about absolute as well in the entire interval. So this is a critical point. Okay, it's a critical point, and you just at this point, what will be here is you have, so x minus x naught into x minus x1. At this critical point, x equals to x naught plus x1 by 2. What will be is equals to, so if you replace x by x naught plus x1 by 2, so first term will be x1 minus x naught by 2. The first term, if you replace x by x naught plus x1 by 2, and the second term will be x naught minus x1 by 2. So that is equals to minus 1 by 4 times x1 minus x naught square. Okay, and you are talking about in magnitude, so the value in the magnitude. Okay, so magnitude in the value is this plus 1 by 4 times this. And let's say, okay, so let x1 minus x naught is equals to h, means the space, means distance between x1 and x naught is h. So then the E1 f, the error in linear interpolation is less than equals to, so that was, the maximum is, so we are going to talk about, so at x equals to x naught and at x equals to x1, the boundary points, they are 0. And this is a positive value, not negative value, x1 minus x naught whole square by 4. So this certainly will be the maximum, right? So if you replace it by this and h, so you have 1 by 2 times h square by 4, h square by 4 time maximum of second derivative. We are not aware about the function, so we are going to replace it by m2. So if I have, this is equals to m2. So you have, this is h square by 8 times m2. So this will be the error in linear interpolation. Okay. Now the next we are going to, let's see error in, let's see in the error in quadratic interpolation. Okay, so let us try to find out the error in quadratic interpolation. So certainly here n value is 2. Certainly here n is equals to 2. So, and then you have the data like x naught, x naught comma f naught, x1 comma f1, and x2 comma f2. Okay, these are the data. And then you have the error is a mod of E2 of f at x. I'm straightforward writing. So that is less than equals to 1 by n plus 1 factorial. So n is 2 here, so 1 by 3 factorial. Okay, 1 by 3 factorial time maximum of f third derivative at z. So that I'm going to replace it by m3. m3 by 3 factorial time maximum of over of the product term, this x minus x naught to x minus x1 to x minus x2. So here you have to also, this is a cubic polynomial. It's a cubic polynomial, and you solve it if you try to find all possible critical points. You will find the two, because the derivative will lead to the quadratic polynomial, and you will get 2 points, 2 critical points there. Okay, and you are taking the maximum over the interval x0 to 2 x2. Okay, so try to identify all those 2 points and see which one will be the maximum. Now we are going to talk about a particular case. So when you have the equispaced data, so let's say we are going to consider the particular case now. How we want to see how the situation will be much simpler if you have the equispaced data. Particular case when you have equispaced data. Equispaced data. Okay, so when you have equispaced data means x0, x1 and x2. If you look at this line, they are means x0, x1 and x2. They are equally spaced, means the length between any one of these x1 minus x0 is same as x2 minus x1. They are equally spaced, that is equals to h. Now if you assume that this is your center of origin, means let's say t, and then this is the previous value, that is t minus h, and that is t plus h. So for finding here in this case, you have, so instead of finding maximum of this cubic polynomial, now you are going to identify, so here in this case here, so you are going to identify the maximum of mod of, instead of that product you have the, now you can just verify t minus h into t into t plus h. Okay, and which is much simpler than previous one, plus h, the magnitude, the maximum of this. So if you see this, if I call this g of t, that is g of t, if you see the product is, this is nothing but t cube minus h square t. Okay, h square t. Then if you put g dash of t is 0. If you put g dash of t is equals to 0, so what are the critical points you will get? So you put g dash of t is equals to 0. This will give you 3t square minus h square equals to 0. This will give you t equals to plus minus h by root 3. Now if you look at here, this is maximum. This maximum is equals to, this is maximum of t square minus h square times t. Now if you replace t by plus h by root 3 or minus h by root 3, that magnitude will make it plus. So it is doesn't means whether you check with h by root 3 or minus h by root 3. And if you fit down here, so what you will get is the maximum value. What it will be is, if you replace everything correctly, that is equals to 2h cube by 3 root 3. Okay, so that is equals to 2h cube by 3 by 3 root 3. And hence this implies the bound on the error in quadratic interpolation, bound on the error in quadratic interpolation, that is mod of e2 f x. So this is less than equals to if you fit all the values, is h cube by 9 root 3 times m3. Just fit the value. Okay, so let's finish this by having 2-3 examples for this. Okay, so let's have examples now, or you can say application. Okay, so you have the following table. So first, let's see that you have the given data set is x and f with value 1 and 2. X value is 1, 1. At 1, the f value is 2, x value is 2, f value is 5. Okay, so predict the value at 1.5, and we have to predict the value at 1.5, and also we need to find the bound on the error. Okay, so you have two data, so you can go for the most linear interpolation. So if I wish to quickly do it, so you have x, and this is f, this is 1, 2, this is 2, 5, and you have the first divided difference, that linear polynomial, right? So that is equals to 5 minus 2 divided by 2 minus 1. So that is 3 by 1, so that is 3. So you have the Newton's form of interpolating polynomial, that is of degree 1. So P1 of x is equals to f of x naught, that is 2, and so that is 2 plus x minus x naught, so that is x minus x naught value is 1, x minus 1 into the first divided difference, that is 3. So that is equals to, you have 3x, 2 minus 3 is minus 1. So the predicted value at 1.5. Okay, so the predicted value at 1.5 will be, so predicted value at 1.5, if you replace x by 1.5, that is 4.5 minus 1, that is equals to 3.5. Okay, now what will be the error here is what we have derived, that E1 of f at x is less than equals to h square by 8. If you recall, that is equals to h square by 8 time m2. So m2 we need to identify by some other estimate, because f is not known to us. So h is what is h is? So if you see h value, that is equals to x1 minus x naught, that is equals to 1. Okay, so x1 minus x naught value is 1. So that is equals to m2 by 8. Another example, you had the previous example only 1, 2, 4. F values are 2, 5, and 17. Then we have derived that the interpolating polynomial was quadratic polynomial, and that was x square plus 1, and that is up. And we have as we have also derived the predicted value at x equals to 3, that is 9. Now if you try to identify the error bound in quadratic interpolation, okay, that is, we have derived that less than equals to 2h cube by less than equals to h cube by 9 root 3 times M3. Okay, but this result was for equispace data. But if you note it down, okay, not down in the table, these are not equispace, because 1 to 2 length is 1 and 2 to 4 length is 2. Okay, so this is not equispace data, so we can't work with this. Okay, so we have to let for, so this will not be working here. So we need to go for that in terms of x only, and we have to identify the possible maxima. Okay, so what is there is mod of, okay, so if you recall, that is mod of e2 of fx is less than equals to m3 by 3 factorial maximum of mod of x minus x naught, that is x minus 1, time x minus x1, that is x minus 2, time x minus x3, that x minus x2, that is x minus 4. Okay, so you have the cubic polynomial, find all the possible critical points, and then you will be able to find the final answer for this. Okay, so we are going to stop down here, okay, for this lecture, whatever we have covered so far. So next we are going to see how this is helpful, Newton's form of interpolating polynomial. Okay, what are the disadvantages of Lagrange's interpolating polynomial? Okay, and then we try to uh, get more simple version of Newton's polynomial. Okay, and then we will try to estimate, which we have left it out, right, m2 and m3, okay, the second derivatives, first derivative, and so on. Okay, so that will be our next in the next lecture. Okay, right.